Welcome everybody to the last day of the Beyond the Boolean Cube workshop. So our first speaker today is Amey Bhangale, and he's going to talk about linearity testing over the p-bias cube. So take it away, Amey.
Okay, yeah, thanks. So I'll be talking about testing linearity over the bias cube, and this is joint work with Subhash Khod and Dor Minzer. So in this talk, we'll be dealing with functions from 0, 1 to the n to reals. Although the workshop is called Beyond the Boolean hypercube, we'll just be talking about functions on the Boolean hypercube. F has a Fourier representation. You can break it up as S, chi-s of x, and chi-s is basically these are all the linear function. What to? Okay, and f is correlated to a linear function. If f hat of s is large in magnitude for some s. And s could be empty set, which is just like it has some bias. Even that function is correlated to a linear function. Okay, so that's that. And so before we start talking about linearity testing over a bias cube, we'll be interested in restriction of a Boolean function. So let me define the kind of restriction that we'll be doing. So let's say mu be a distribution on just the bits. And let's say I can write mu as alpha times the uniform distribution plus 1 minus alpha times the remaining distribution. Okay. The remaining like residual distribution. So I'm just like isolating the uniform distribution from the rest. The restriction, which I'll be denoting by this I and Z. Okay, so it is as follows. First, select a subset I of n by including j in I with probability 1 minus alpha independently. Okay, so we are basically selecting a subset of size 1 minus alpha times n, and then select z, which is in 0, 1 to the n minus 0, 1 to the I, according to the distribution nu. And the restricted function, so the restricted function which I am denoting it by fi restricted to z, it is a function from 0, 1 to the n minus I to reals. This is defined as f x is f evaluated at x. We are basically restricting the coordinates from I according to z, and then you have these live variables. Okay, so f, you have this I here, you are putting z, and then in n minus I, you're putting x. So that's the definition of a restricted function. And we are interested in understanding the properties of restricted function. You know, what if we know something about the restricted function? Can we deduce something about the original function? Okay, so let me define. So the question that we're interested in, if the restricted function is correlated to a linear function, then what can we deduce about f? Okay, so that's the question. Okay, so what can f be? I mean, f can be a low degree function, because if you just restrict, and in this talk I'll be thinking about alpha as some constant, you know, like say 0.2 or something. So we are really restricting like constant fraction of the coordinates. Okay. And so if the original function is a low degree function, then if you do this restriction, then the bias of the function, the restricted function becomes large, or the function becomes constant most of the time. In which case the restricted function is correlated to a linear function, right? So low degree function is one case. F can be a low degree function. And when I say low degree function, it's the degree is independent of n, some constant, just depending on yeah. So in this talk, all these epsilons and deltas and etas, they are constant, independent of n. Okay. So we are saying that once we do the restriction, f is correlated to a linear function in that sense, then f can be a low degree function where the degree just depends on that. What is another example? Another example is f can be a linear function. Right? I mean, if you have a linear function, if you just restrict a few coordinates, then the restricted function becomes a linear function. And the main theorem that we show is these are the only two cases. So let me write it more formally. So probability over the restriction I and Z, there exists S such that the restricted function is correlated to this linear function. It happens with significant probability. Then F is correlated to a product of low degree function and a linear function. Because I mean, it can be this, it can be this. So you can even combine these two examples. Just take f as the multiplication of low degree function and linear function, and it still has that property that with significant non-negligible probability, the restricted function is correlated to a linear function. So is the statement clear? So in other words, we can write n f chi s and g is large, where this is a linear function and this is a low degree function. And in fact, we can also take g to be just the low degree part of this function. So any questions on the theorem statement? Okay, so so the rest of the talk, this is the plan of the rest of the talk. So one is I'll show how to use this theorem to prove linearity testing or a bias cube. Application to linearity testing or a biased cube. And second, I'll probably say a few words about how we prove that theorem. Techniques. So let me first define this problem of linearity testing, and let me tell you what was known and what is new. So we are given this function f from 0, 1 to the n, and in this case, let me switch it back to 0, 1, the Boolean thing. And we want to test whether f is a linear function or f is far from a linear function. And so this is an actual test. So select x, y uniformly at random. Let z to be x plus y, and check if f of z is equal to f of x plus f of y. Right? That's the BLR linearity test. And and there are two interesting regimes. One is the high acceptance probability, and one is the low acceptance probability. So the high acceptance probability regime is called 99% regime, which is basically if the test. So this is a test. If the test passes with probability 1 minus epsilon, at least, epsilon is a small constant, then deduce that f is close to a linear function. And there is a 1% regime, which is the same, except that the test passes with probability half plus epsilon. Epsilon is some constant greater than 0. Then deduce that f is close to a low degree, f is close to a linear function, right? And this was answered by Blum, Luby, and Rubinfeld in 90, and this was answered by Bellare, Coppersmith, Hastad, Kiwi, Sudan, I think in 96 or something. So we know, so that's what we know. So let me move to the biased linearity testing. So this is again the same problem. We want to test whether f is a linear function or f is far from a linear function, but we are restricting ourselves to the case where each of the queries, they are distributed according to a p-bias distribution. So here in this case, each query is distributed uniformly, but in a biased linearity testing, we fix a bias parameter p in 0, 1, and we are interested in a test where each of the queries, doesn't matter how many places you query f at, but we want each of the queries to be p-biased. Okay. Each query is distributed according to a p-biased measure. Okay. And so let me tell you a bit of history about what was known about the p-biased linearity testing, and then then I'll state the main result, or one of the main results, which is biased linearity testing from this paper. So known results. The first one is by Koperty and Saraf, 2008. They give or constant query linearity test in the 99% regime. Right? I mean, if the test, they design a test, and the test queries some constantly many points, and if the test passes with 1 minus epsilon, then they conclude that the function is correlated to a linear function. Yeah, this is a different test. Yeah, that. Then so I won't try the name.
So could I ask something?
Yes.
What is correlation here?
It just f. In this case.
In the p-bias case.
Yeah, in the p-bias case, correlation just means that mu p to the n f is correlated to the character being large. Right, because we are just doing like p-bias testing, so everything sits on the pth level. So there we ask whether f is correlated to this character. Or
if x and y are mu p, then z1 will be mu p.
Sorry?
If X and Y are MUP, then Z1 be
No. So that's not the test. This is just like an example of a test, just to motivate what was known. And here I didn't even tell you what the test is for now, but I just defined it. We want a test where each query is distributed according to p-bias measure. But yeah, that's not the test.
So
Yes.
so in the uniform case, are the you actually query X, Y, and Z, right?
Mhm.
So they are correlated, but you want to make sure that each individual one's marginally is uniform measure.
Mu p measure. P bias.
P is a half.
In this case, p is a half, but I'll give you a p which is 0.2, and then I'm interested in a test where each query is distributed according to mu p measure. So that's the bias linearity test. So I fix a p, which is anything maybe other than half, and then I want each query to be distributed according to the p bias measure on the Boolean applications.
The correlation you wrote according to mu p, the characters are now different.
No, it's the same. The product of linear functions, product of variables.
They're not the bias characters.
They're not the bias characters.
So if you remove the condition that the queries need to be p-biased, does the problem become trivial?
We have linearity testing for that.
No, sorry, no, but the correlation still should be under p-bias, but the queries don't need to be.
Then, yeah, I mean, it's not clear then, because if the queries are uniform, you're really looking at just f defined over the middle slice, or around that
Like what if I can choose, what if I can use randomness to choose the queries?
I think still, I mean, you would still be querying f over some slice, I mean, within some slice, and then you can really put anything over here, and your test won't even touch these points.
It's a two-function test.
Yeah, if you have two function tests, yeah, then you can. But if each of the queries is uniformly distributed, then you won't even touch that part or that part of the slice. So it could be anything. So there's no correlation between the test passing probability and f being close to linear. Okay. Okay, this is what we knew, and then the paper by David, Dinur, Goldenberg, Kindler, and Schinkel in 2015. They gave a 3-query test over a slice, which is morally same as the p-biased. I mean, a slice meaning that you fixed a slice, the kth slice, and you want all the queries to be from the slice. F is really defined on the k slice, and then you want to understand whether this is correlated to a linear function or not. And they gave a 3-query test over a slice, again, which is similar to that, but in the 99% regime. Okay, and recently, there's a paper by Dinur, Filmus, and Harsha, I think from 20. They gave a 4-query test in the 99% regime. I mean, I already said that this is more or less same as p-bias, but what is new? I mean, they didn't just give a linearity test. They gave a 2 to the d+1 query test for low degree function, for degree d function. Okay. So if you just apply that to linear, you get that. So okay, so far we only knew linearity test or a p-bias cube in the 99% regime, and the main theorem and the main result is that we have now a linearity test or a bias cube in the 1% regime. But okay, I mean, there are some caveats. So fix I mean, it doesn't work for any p. So it works for p in between 1/3 and 2/3. There exists a 4-query p-bias linearity test. In the 1% regime. And I mean, as usual, the test has perfect completeness in the sense that if is indeed a linear function, the test passes with probability 1. If it passes with probability half plus delta, for delta greater than 0, then we conclude that f is correlated to a linear function. So, so now let me try to just, so this is the random restriction theorem. So in the next few minutes, I'll just try to motivate, at least, I mean, my plan is just to show that how to use this theorem to prove something of this sort, you know, and the proof will be very high level. It's just that I just want to highlight the connection between this theorem and that theorem. That's it. Okay, so next, random restriction theorem to bias linearity testing. So, so that's so our test is 4 query, which can be defined as follows. So you have a distribution nu on 0, 1 to the 4. Okay, such that a plus b plus c plus d is equal to 0 if a, b, c, d is in the support of nu. Okay. And then we're going to sample x, y, z, w from 0, 1 to the n, the 4 queries, such that, I mean, coordinate wise, it's an independent sample from nu. And by definition, because we have this property that, you know, every tuple which is in the support of nu, the addition is 0. By definition, we have w is equal to x plus y plus c. Okay, and the queries and test if w is equal to f of x plus f of y plus f of z. Okay, so that's the test. So we have a distribution on 4 bits. We just 4 queries are basically coordinate wise. You just put like a sample from mu, and then you just repeat it n times. Okay, and for technical reason, we want mu to be pairwise independent, and that's the reason we have these conditions on, I mean, this condition on P. Okay. Sorry. Yeah, and definitely, yeah, and marginally T biased. Okay, so if you have this condition, yeah, you can't have like P less than 1/3 and pairwise independent distribution, but any P, if you give me any P in between 1/3 and 2/3, I can have such a distribution which is pairwise independent, and marginally it is P biased. So all my queries will be P biased from the P biased measure. Question? Yeah. Okay, so now let's say we have this function given, and now in this case I'll switch to +1 -1 world, and f passes the test with probability at least half plus delta. Delta is some constant greater than 0. Okay, now this can be written as this expectation over x, y, z, w, f of x, f of y, f of z, f of w is at least delta. Maybe it's at least delta, maybe it's delta over 2. Okay. Now the thing that I mean, the main thing that we would like to do is that somehow we would want to analyze such an expression where each query is distributed uniformly, because we know how to analyze such a test, which is really the 4-query linearity test, where each query is uniform, like x, y, z uniform, and z is equal to x plus y plus z. We know how to analyze such tests, right? So, so that's how we. So in order to reduce to that case, we'll write nu as some alpha times the uniform distribution on the 4 bits plus 1 minus alpha times the residual distribution. And what we'll do is we'll first choose some 1 minus alpha fraction of the coordinates independently, like, you know, and then set these values according to nu tilde. Okay, and then on the remaining coordinate, we'll just sample like a uniform 4-bit string whose addition is 0. So I can write this as expectation over I, which is 1 minus alpha times n. Then I have A, B, C, D. These are the restrictions. And then I have another x prime, y prime, z prime, w prime, f of ax, f of dy prime, f of cz prime, f of dw prime. Okay, so I didn't really do anything. I just changed the. So here it was according to new tensor n. So ABCDs, they are according to new tilde tensor n, and these are according, not n, maybe I, and this is according to the uniform distribution. Not really the uniform over A plus B plus C plus D is equal to 0. Okay, so this is our uniform tensor I n minus. Right. But again, I mean, in the picture, it just says that, it just means that I first select these coordinates, then fill in these entries according to nu tilde, and then the remaining I just filled in according to the uniform distribution on the 4 bits. Now this expression, this is really the restriction of f. This is really the restriction. I mean, you can really think of this as restricting the I coordinates of f to a, and restricting the I coordinates, I mean, coordinates from I to b and c and so on. So this is same as for a typical I and I. This is same as prime, y prime, z prime, w prime. This is according to the uniform distribution. Right, so far so good. And now here x prime, y prime, z prime, w prime, they are distributed uniformly according to the where, I mean, each query is uniform here. X prime is uniform, y prime is uniform, z prime is uniform, and w prime is just the sum of this, which is also uniform. And we know how to analyze such an expression. From this we can conclude, let me write it. So from this we can conclude that for a typical I and A, is large. And this is just the, I mean, this is again the standard linearity testing analysis. Yes.
X prime, y prime, z prime are independent.
They are not independent. I mean, you can think of x prime, y prime, z prime are independent, and w prime is just the sum of these.
But the original distribution was only pairwise. Why it's supporting the? It seems
It's a miracle. It's a miracle that happened when p is equal to 1/2, then all of them become independent. You can calculate it.
I mean, U is a uniform distribution over the support, right? Why it's a support?
So, I mean, so if it is a pairwise independent distribution, then you have all these strings. And again, I mean, when I said new had a full support, by the way, where a plus b plus c plus t is equal to 0.
Okay. I mean, they're selected uniformly under the condition that the sum is 0, but
Still, each one separately is uniform. Actually, each three.
So that's the conclusion that we got, that for a typical restriction, the restricted function is correlated to a linear function, and that's where we use the main theorem, that if you have the condition that for a typical restriction, the restricted function is correlated to a linear function, then the original function is correlated to a linear function and the low degree function. So from this, we can conclude that not only this, expectation of S1 G1 of G1 2 G3 G4 is large. So I just write delta here, but it's some function of delta. Okay, so I mean, so I did a very big jump from this expression to that expression, right? I mean, all I knew at this point is that f is correlated to such a product, such a function. But it need not be the case that there are only constantly many such product functions. If there are only constantly many, I can write f as sum of that thing, this as sum of that thing, and then I can just find one from each of these things where I can replace f with this and still hope that this expectation is large. But you can still do some sort of argument where all such correlated product functions, the size of that is small, some constant. Okay, but in general, it's not true. Yes.
The green theorem, how is delta prime depending on other things like delta epsilon?
So it's just some function of delta and epsilon. So
So the order is like polynomial.
So I don't quite remember so is it polynomial?
This type is like exponential.
Yeah, here we didn't care about the dependency, but I think in the next paper we have some exponential in one over. Yeah.
So constant.
It's still constant. Okay. So yeah, so each of these functions, they're correlated to a product of low degree and linear. So we just moved from this to that. Again, I'm just hiding something. It's not. I mean, you need to do something to conclude this thing, but let's say that can be done. And we also use the fact that GI, this is really f times chi SI and the low degree part of that. Right? That's what the theorem gives. And you can also take. It also gives you a structure on the low degree part. So, so if expectation of GI is large, then we can conclude that f is correlated to a character, right? Because that's this. So if this has a large bias, it means that f is correlated to bias. So you assume that all the expectations are small. We can also conclude. We can also from this expression, we can also conclude that all the SIs they should essentially be the same. You can't have like very different SIs because then there is some randomness in the coordinate that is left, and then this expression will become very small. So all I'm saying is that SI, SJ, this is small. Again, small just means some constant independent of n as a function of delta. So this expression essentially boils down to some low degree function G2, G3, and G4 being large. So again, so the main thing is that this is the step where we use the random restriction theorem, and then from that we concluded that now we have a product of low degree functions whose expectation and the expected product of low degree functions is large, right? And now this can't be true because why can't this be true? There's a big hammer that we need to use, but this leads to a contradiction. And the big hammer is the Mosel's invariance principle. So we know that each expectation is small. So by invariance principle, and assuming and using the fact that the distribution nu was pairwise independent, this is same as product of expectation. And here we assume we need that nu is pairwise independent. Okay. Yeah, and once you do that, this expression is small because we assume that all the biases are small, right? And that leads to contradiction. So, okay, I mean, I did a lot of hand wavy stuff, but I just want to point out a few technicalities. So you can't really apply Mosel's invariance principle for these functions because these are just truncated functions, so they are not bounded. Okay, but that can be taken care of by using some noise operator. Another technical issue is that you need the functions to have low influences, right, to apply the invariance principle. And again, that can be done by restricting a few coordinates, few influential coordinates from these functions. And also, we also assume that GIs, they are not correlated to linear functions to begin with, right? And because of that property, we can restrict like some constantly many coordinates and make sure that all the influences are small. The boundedness can also be taken care of. And after that, you apply the Mosel's invariance principle. So that's the proof of bias linearity testing, assuming this theorem. So any question? Yes.
So here, what's the point of using like a 4 tuple? Like if I, let's say, pick 5, like a 5 tuple, and then I check whether like C5 is
yes.
F of, is that harder to analyze, or does that give you a weaker?
No, I mean, it will still be, I mean, I mean, the analysis would be the same, but you will end up querying five locations. So typically the number of queries is also important. So, I mean, you want the number of queries to be as few as possible.
But I think wouldn't that give you a weaker condition on the key? You have like more.
Yes, that will. So yeah, if you are willing to increase your number of queries, then you will get the linearity test for different keys. Yeah. Right. I mean, all we want is some distribution such that it is pairwise independent. Okay, so I still have 20 minutes. So in the remaining 20 minutes, I'll try to basically sketch a proof of this theorem. And again, the sketch will be very high level. It's not going to be. I mean, okay, so the whole point of now actually proving this is to introduce some direct product testing statement. So if I can just do that, I think that would be good. So that's my aim, just to analyze this and leave it at some point where you need some direct product testing result, and then I'll just probably leave it at that. And I think I'll mostly draw pictures to prove this theorem. I won't really draw anything. So let's see. So what kind of condition we have? The assumption is that for a typical restriction, there is a Fourier coefficient which is large. Okay. So these are my coordinates 1 to n, and for a typical restriction I and z, I have some Fourier coefficient which is large. This is the set S. Okay, so this just means that f hat of I restricted to z at S is large. You can say that assuming if h hat of t is large, then for a restriction h j restricted to y at t intersection j complement is also large. all I'm saying is that if you have an original function, if some Fourier coefficient is large, then if you restrict a few coordinates, then the same Fourier coefficient stays large in the restricted function with some decent probability. Okay. So using this fact, we can conclude that so there was this I, this was Z, and if you further restrict some other coordinates I prime to some other Z prime, then the same part of S, it stays heavy in the restricted function. So F where I restrict I to Z, I prime to Z prime, S intersection is large. Sorry?
Maybe it's better to write S subscript IZ because S I and Z.
Oh, right. So S depends on I and Z. Yeah, sure. Yeah, I mean, this really depends on I and Z. Okay. And again, this is a typical scenario. It just means that if you select I randomly and I prime randomly, and then select Z and Z prime, then typically this will be large, starting from our original condition. Okay. And then if you use Cauchy shorts, then you get that not only this happens, you can also re-randomize the Z prime part here. Z, I prime, Z prime, and then you can still hope that the same coefficient stays heavy in that. So here I'm just re-randomizing the restriction to I prime. Do you see this? This is probably just some, I mean, Jensen or convexity Cauchy shorts. So what does that tell us? So if you have this set I and I prime, and there is this restriction where you restrict I part to Z and I prime part to Z prime. And in this restriction, you are restricting I part to the same Z and I prime to some other Z double prime. And the same coefficient stays heavy in both the restrictions. Okay, which just means that for I union I prime, a typical restriction for a typical restriction Z prime, the same Fourier coefficient stays heavy.
But there could be several
Sorry, what is the question? In this case, I mean, so you can't have several Fourier coefficients that are heavy too often. So yeah, I mean, I'm assuming that the norm of F is bounded, you know. So whenever I say this thing, this happens also with some non-negligible property. Okay, so I'm, yeah, yes, yeah. Okay, so why is this true? Because I mean, if for I and I prime, if the set of Z tildes for which the restricted function is correlated to this is small, then using the small set expansion problem, I mean, you should really think of Z prime and Z double prime. These are just a correlated copy. I mean, this is a correlated copy of that, right? So if for very few restrictions Z tilde to I and I prime, if this Fourier coefficient is large, that means that if you select Z prime and a correlated copy of Z prime, then it goes out of this window. But but we know that that's not true. I mean, even if you take the correlated copies, the Fourier coefficient stays large. So we can really define, now we can really forget about Z prime and Z double prime. So for I union I prime, collect all the heavy Fourier coefficients. And when I say heavy, it means that it stays heavy for a typical restriction. Okay, and then you can say that this list is bounded. So I'm going to now state this fact again, which I'm not going to prove, and hopefully this is the end of hand wavy stuff, and then we'll I'll state the direct product result. So that's the last hand wavy stuff. So you have I and you have this I prime. Okay, and then we said that there is some Fourier coefficient T that remains for a typical restriction of I in an I prime. You can also say that you can re-randomize the I prime part. Let's say I choose I prime to be this, I double prime. And then the same part of this coefficient, it stays heavy in this restriction. So the same thing stays heavy. So if you look at the set of live variables and look at the Fourier coefficient that was heavy here and that was heavy here, they agree on the set of live variables. Okay, and again, this is some sort of Cauchy-Schwarz kind of thing. I mean, you have to do it carefully, but so yeah. So okay, so if you believe me, if you believe that this happens, which is saying that I'm selecting I prime, the same I and some I double prime, then this sort of same Fourier coefficient stays heavy for a typical restriction of I prime and I double prime, then we would like to conclude something of this sort. F is correlated to a character, and this is really a direct product testing result. So how is that? So so I can define a function on n choose n minus what are the size of I prime to so all I want to do, so I want to define a map which is basically 0 everywhere and then 1 on the heavy Fourier coefficient and 0 everywhere. So for I and I prime, I would get this bit string, and for I double prime, I would get 0 0 0 0 1 1 1 1 1 0 0 0 0 0. And we have, so if I define a map like that, I mean, for a given I prime, there are many such coefficients bounded. You just select one and then assign that value here. And the fact, and this condition that we arrive at, it's same as saying if you select a random I prime and restrict this to so let me call this set, the set of live variables here is A and the set of live variables here is B. So this is same as F of A restricted to A intersection B is same as F at B restricted to A intersection B. So the set A is basically the set of live variables here. And set B here is the set of live variables here. So we are basically assigning to a set of live variables the Fourier coefficient, which is heavy. And this property that the same Fourier coefficient stays heavy in a restriction for I prime and I double prime, it can be stated as if you select these two sets, then on the intersection, there's a decent chance that they agree with each other. Okay, and this is really the, I mean, and we are in the setting of the direct product testing result. So, okay, so I did a lot of hand wavy stuff. So, but let me just write now a clean statement of direct product testing result that we are interested in and that we can use, hopefully use here. And yeah, and then I'll probably state a couple of results that were known about the direct product testing and what is the difference between our result and that result. So any questions so far? Okay, so what is the setup for a direct product test? You have a table which is defined on every k size set. It gives every subset of size k a string from 0 to the k. And you should really think of this as assigning bits to like the coordinates in S. And you want to test if F is coming from a global string. It just means that does there exist A, which is a bit from 0 1 to the n, such that F at S is really the restriction of A at S. Okay, this would be like the, okay. So how do you test if a given map is such a direct product? There's a natural test, which is select A and B from n choose k. These are sets of size k such that the intersection size is say at least k over 10, and then check if f of A at the intersection is same as f of b at the intersection. Okay, so if f was indeed coming from a global string, then this would just be the A at A intersection B, and this would be the string small a at A intersection B, and then this check passes, right? Okay, so the known results, at least comparable results, is there's this result by Dinur and Goldenberg from 2008. Says that if the test process with probability at least epsilon, okay, then f is close to a direct product, to a global function. So let me just write down this. So what it means is that for at least some epsilon prime fraction of sets f at s, so okay, there exists a global function g from n to 0, 1, such that for at least some constant fraction of, constant as in just the constant depending on epsilon, fraction of the sets, this string agrees with the global string on all but constant fraction of the coordinates. So if I take the probability over I in S, I is same as G of I, is at least 0.9. So it's important that the kind of agreement they get here is that for poly epsilon fraction of the sets, your table agrees with the global string on constant fraction of the coordinates. That's constant fraction. Okay. And another relevant test is, so this is like the test in 1% regime. And then there's another test by Dinur, Harsha, and Filmus from 20 that says that if f passes the test with probability 1 minus epsilon, again, this is the 99% regime. Right? If the test passes with like almost close to 1 probability, then there exists a global G such that for at least 1 minus some epsilon prime fraction of S, here you get full agreement. F at S is in full agreement with G at S. So okay, so before stating our direct product result that we need for this, just let's compare these two results. So this is in the low acceptance regime, it's like very weaker guarantee on the table, and then they conclude that for some epsilon prime fraction of the sets, the table agrees with the function on constant fraction of the coordinates. And here the starting assumption is much stronger. The test passes with probability 1 minus epsilon. And the guarantee is also much stronger here. It says that for at least some 99% fraction of the sets, the table fully agrees with the global function. Okay. And what we show is that we show we give a direct product test in a 1% regime with a much stronger conclusion than that. So let me just state that. So in our case, we need k to be some constant times n. Okay, it doesn't work for any k. In fact, yeah. So in our setting, k is some constant times n. Q is a constant. What we show is that if again the same test, the test passes probability is epsilon, which is some constant independent of n, then there exists a global function g that for at least epsilon prime fraction of the sets S. Again, this epsilon prime is just some function of epsilon. This agrees with G on all but some many coordinates. So, okay, so the difference between this and that is that here the guarantee is on constant fraction of the coordinates. So there are still like some 0.1 times k coordinates from S where they differ. And here we have a stronger guarantee. We are saying that F agrees with the global function on all but constantly many coordinates. Okay, and that constantly many coordinate, it features into the degree part of the restriction, the random restriction theorem. So I mean that was needed because yeah, so we wanted the correlation to a low degree function and a linear function. So the low degree part is really coming from this bound. Okay, and you cannot really hope such kind of a stronger statement in this regime, right? The example is very easy to construct. So maybe I can just state that example. So you can define a table from n choose k to 0, 1, such that 0 1 to the k, where f of a is used. So that you fix some global function n. Okay, and now I'm defining the table f, which is really g at a plus I add a little bit of noise, which is a string from 0 1 to the k whose support is some log 1 over epsilon. I'm just like setting this table according to some global function, but I'm adding some small Hamming weight noise in it. Now, if you select your set A and B, okay, then there's a poly epsilon chance that, or epsilon chance that the noise will not appear in the intersection. And the table will, I mean, this table will pass this test with poly epsilon, but there's no global function where f agrees on all the coordinates. Okay, so that's I think, yeah. So let me end my talk here.
Questions for Amey?
Prevents you from doing this for, say, smaller p, maybe with a little bit more query?
Yeah, you can do that. Yeah, if you increase the number of queries, then you can go. But we already have a constant query test for every p, the Kuperti-Saraf test. The number of queries is a function of p, and then that test works for all p's. So we already have such tests. But if you really want to get like 5 query tests, what the smallest p I can get, then yeah, you can do that.
Or the 3 query test?
3 query, we don't have pairwise independent on 3 query. So that is still.
So is it even like theoretically possible?
Is it even theoretically possible? I don't know, maybe, I don't know. Somehow you can cook up your queries that are p-biased, and I mean, you can always do something of this sort, right? So you have these coordinates, you just first select some 2p coordinates, and then inside that do your usual BLR test, right? So each query is p-biased, and you can get that this is correlated. But then you need to like lift it up to your original function. So that it's not clear.
Any more questions?
Yes.
Why do you need the queries to be p-biased?
I mean, that's the definition of a problem. So I didn't really motivate, why we want the queries to be p-biased, because okay, so I mean, p-biased measure are used in many things, to understand sharp thresholds of graph properties. It is also used in many not many, but a few hardness approximation results. So understanding some test or p-biased measure is an important problem. So that's the motivation for studying this problem. Yeah.
Okay, if there are no more questions, let's thank Amey again. And we'll return in 30 minutes.
It's very long.